In this video we're going to focus on the first topic in Unit 3 of National 5 Chemistry, and that is metals. And specifically in this video we're going to focus on metallic bonding, and we're going to talk about how different metal atoms will bond together. Now up until this point, particularly in Unit 1, we have focused on what the electrons do within atoms. We've focused on atomic structure, and throughout those topics we've spoke about how the outer shell electrons, so the outer electrons at the very edges of the atoms that we're thinking about, are very tightly held in position because of those negatively charged electrons being very attracted to the positive nuclei of the atoms that they are orbiting. Now, in this case, it's going to be slightly different. So let's run through what we already know about different types of structure, different types of atomic structure, and then we can compare that to how metals have different structures. So if we think about where the electrons are, we can consider an element. Let's just take lithium for example, which happens to be a metal, and let's think about lithium as a single atom to start off with. So if we find lithium in the periodic table, we will find that it has an atomic number of 3. Now what does that mean? That means that lithium has 3 protons, 3 positively charged subatomic particles in the nucleus of the atom. And it also means it has 3 electrons, because atoms within elements have to have the same number of protons and electrons. They have to balance each other out in terms of their charges, so that the overall charge of the atom is 0, because atoms are neutral. So if we go back to this diagram and identify where those electrons are, we have 2 electrons in this first shell of electrons, and that first shell can only hold 2 electrons, remember. So to fit in the third electron, we have to go to a second shell, and we write it like that. I'm using little x's to show where the electrons actually are. And that is what an atom of lithium might look like in terms of its electron configuration. 2 and then 1. Now if we were to take that lithium atom and we were to form an ionic compound, an ionic bond with a non-metal atom, for example chlorine in this case, we'll find that in terms of its electrons, its outermost electron in lithium is going to move from lithium and be taken by the chlorine atom to form a chloride ion. In doing so, the lithium, because it's lost a negative electron, will become positively charged overall. And because the chlorine has formed a chloride ion and has gained a negative electron, it now has more negative charge, it will be negative overall. And the formation of those charges, the formation of these ions, these charged particles, forms this electrostatic attraction between the 2 ions. This positive and negative charge are attracted to one another, and that forms that strong bond. But still, the electron movement is very specific. We take an electron from the metal and it moves into the non-metal and nowhere else. That chlorine is now a chloride because it's taken that electron, it holds it tightly in its structure, which in turn makes the lithium ion very attracted to the chloride ion. Now, if we were to take lots and lots of lithium atoms, we now want to think about what that would look like. Because if we have a metal, such as lithium, that is basically what it is. It's lots of these lithium atoms all bonded together. But what happens when it's not got a non-metal that it can donate that electron into? What happens to that electron? What happens to the rest of the electrons? That's what we want to discuss in this video. So, when we think about metallic bonding, we have metal elements, and in those metal elements, the electrons, which I'll use the letter E and a little negative sign for, in the metal, are said to be delocalized. So we're now not thinking specifically about electrons in orbitals, we're thinking about them being removed from those orbitals, sort of floating around. They're not localized to a specific atom, they are delocalized. So they're moving around more freely. So they're said to be an array of positively charged ions surrounded by a sea of delocalized electrons. So some complicated words going on here, so we're going to look at a diagram to understand what is happening a bit better. So if I were to zoom in with a very powerful microscope to a metal structure, I would find that there is indeed this array of positively charged ions, which are essentially the nuclei of the metals and most of their electrons, so the inner shell or inner shells of electrons, depending on how many electron shells there are. But what happens to the outermost electrons? So if I go back and look at my lithium diagram, it would be this electron here for every atom. That outermost electron is delocalized. So they're all sort of swimming around the positively charged ions, moving around freely in this sort of sea or pool of delocalized electrons. Now, since the electrons in this pool don't belong to any particular ion, like they were in the atom or in the ionic compound, they're not tied to any given positive ion, they are free to move from one ion to another. So they move along like a sort of sea along the positively charged ions. Now that is very important because that concept, that idea that they move around freely, explains electrical conduction. It explains why metals are very good conductors of electricity. So metals can conduct electricity in any state, whether it's a solid, liquid or a gas, because of these delocalized electrons, because of the fact that the electrons are free to move. And we could test that. We could test that simply using a metal and placing it in a simple circuit with a battery and perhaps a bulb that would show whether the circuit is complete or not, passing through the metal. And of course the bulb would turn on if the tested material was indeed a metal. So in summary, when we're thinking about metallic bonding, that is what is very important to remember. Overall, the structure of metals, so metallic bonding, is regarded as a regular array of positively charged ions surrounded by a sea of delocalized electrons, with each ion being attracted to the pool of electrons around it and vice versa.